Hey, my name's Bill Kennedy, and today I want to start to share with you some of the AI-related stuff that I've been learning over the past couple months. I'm at a point now where we've actually built a really cool Connect 4 game that eventually you'll be able to see on ardenlabs.ai, but there's a repo too you'll be able to download and play with it. We'll put all that stuff in some of the notes. But it took me a while to be able to wrap my head around these different AI level concepts. And I thought it would be fun to share those with you and sort of walk through the same steps that I have sort of gone through right there from the early beginning. And so this is video one. This is where we're going to sort of start. And where I started was with the idea of vector databases and vector embeddings. The vector databases are really important technology as it relates to working with any sort of AI solution. We have LLM models, or large language models, that we're going to work with. But as you'll learn at some point, these models are really dumb. They're only as good as the information that either it already contains or we feed into it. And our vector databases give us the ability to make them smarter. And I want to show you some of that. But we've got to still get a basic understanding of what a vector embedding is and sort of how it works semantically in the entire space. So we're going to start there with a real simple handcrafted solution. And hopefully by the end of this, you'll have a better generalization understanding of what the vector database is and what it's going to do for us. And we'll continue to sort of build our vector knowledge as we go through these examples and eventually do something with the LLM as well that gets interesting. So let me switch over to my laptop. This is the AI training repo. This is still a work in progress. There's things I'm moving out of here and all of that, but AI training from the Arden Labs GitHub. So you'll see this stuff here, and I've got that repo open already, and you'll see a folder with a set of examples. And we're going to start there with example one. And the idea of example one is to really wrap our head around what a vector database is giving us, what a vector embedding is, and all these things. And maybe what I want to do is maybe give you sort of a visual understanding first before we do anything else. Here's the general idea. What if I draw a simple sort of graph in 3 dimensions, just to sort of start. So we've got our X, right? We've got our Y, you've got your sort of Z. So, and what that ends up giving us is this three-dimensional space, right? Like, that's the idea. We have a 3-dimensional sort of space. Maybe this line is a little bit better if I do something like that. We'll see it more. We've got this 3-dimensional space, and the idea of generating a vector is that we could find things that are similar to each other in a space. So when I think about embeddings, I'm thinking about there's some space, like the space that I created here. And what we're going to do is take data, whatever that data is. It could be full paragraphs, it could be images, it could be anything in the world that we've been able to digitalize. And the idea is that we generate some sort of vector of that given piece of data, and we're able to sort of plot it in this space. So maybe what I've done is I've taken this data, maybe it's an image of something, we've vectorized it, and it plots sort of there in space. Maybe this one plots here, while these sorts of things that we're now, say, plotting, plots over here. And we just continue to do that, right? And so for every sort of piece of data that we have, we can vectorize it and sort of plot it in space. Now, the idea is that the items that are plotted near each other, right? So maybe I'll use a square for this for a second. So these things right here, right? They're close to each other in terms of where we plotted them in space. And so the idea is that these things here should be more similar to each other as a paired. So these two things should be more similar as compared to maybe this and this, right? That's not very similar. And so the general idea is that we want to be able to vectorize a piece of data, plot it in space, and then identify which pieces of information are similar to each other, and then be able to leverage that in an intelligent way. What's one way we can do that? Well, one of the final examples that we'll have with these videos, we'll be taking my book, my Ultimate Go notebook. Here's the book right there, right? And this book's going to have a lot of content. And so one of the things we're going to do is take pieces of that content and we'll vectorize it, right? So maybe these two pieces of content were sort of close together in the book, but this was from a completely different chapter in the book. That's the idea. And then maybe we can ask a question to the system. Maybe we ask a question about interfaces. And what we want to do then is try to find those items in the book that are related to interfaces. Maybe these are the items that are related to interfaces right here, right? And so the idea then is I should be able to ask the vector database, what sort of, right, what embeddings do we have here in space that are similar to interfaces? We would hope that the vector database would bring back these two items. And then those two items we could feed to an LLM to be able to, say, respond in an intelligent way. So hopefully that gives you a general idea of why the vector stuff is so important, these vector embeddings and the similarity. Because we're going to be chunking tremendous amount of data around us, and we're going to want to be able to find similar data to maybe questions that are being asked, and then we want to be able to leverage those smaller pieces, even for some just better performance, better accuracy, better responses. And so what I want to learn first is, you know, how do these vectors at some level work? I mean, we've got algorithms here that use what's called cosine similarity. The algorithms are there. You could dig into them. Some of that math is beyond my pay grade, but it's there. But more importantly, how do we even sort of begin to understand how these things can be plotted? So sort of with that in mind, let's take a look at this first example and see if we could get a general semantic understanding of what's happening. We're going to start here on line 36. What I'm going to show you isn't anything that we would do in a real sort of AI system, right? These large language models that know how to create a vector for an embedding space, we would never really know exactly underneath the covers how it's doing that, right? We can test that it's working, but I'll show you how, right? They wouldn't be accurate if we were able to really peel you need thousands of millions of points of data. But I want to get us to a point right now where we can sort of wrap our head around the idea. So let's pretend that our LLM, right? Let's say that we're going to create our own sort of embedding system. But because we're doing it by hand, we're going to tailor this to essentially these 5 features, okay? So again, this would only let us create similar embeddings within the scope of these 5 features, nothing that we would be able to, or be able to use in a production system, but it will give us that idea. So in our case, we're going to have this idea that we have something, we name it, and then we're going to give it a score on how much authority this thing has. We're going to give it a score if it's an animal or a human, whether it's rich, and whether it's, let's say it's gender, male or female. We're going to have a very specific sort of feature set that will let us identify similarity in the data. So that's our data right there. And then on line 46, what we're going to do is we're going to create a vector of those 5 pieces of information. So our vector is going to essentially have 5 points. Now, when I gave you the diagram before, we were sort of doing everything in 3-dimensional space because, I mean, that's what we can picture in our head, 3-dimensional space. But you'll learn that our vectors can be as high as, 1,000 different points of sort of accuracy in terms of what it represents. So in our case, it's just 5 points, right? Our vector is based on a floating point number related to authority, animal, human, rich, and gender. At some point when we use Ollama, one of the embedding models in Ollama, we'll get back 1,024 points. We won't know what the features are. We just won't. But we will be able to see that regardless of what the features are from this particular embedding model, we're going to get the same sort of accuracy in terms of similarity. But just imagine right now that we're doing this by hand, so this is what we're going to base all similarity on: authority, animal, human, rich, and gender, okay? And then based on that score. So you would think that data points that had a similar authority, right? Similar animal, human, similar rich, you could start to see how they could potentially plot closer to each other. Okay, so let's manually define some data. So we'll define something called a horse. And you can see here that that horse has no authority, but it is an animal. It's not human. It ain't rich. And we're just going to say that this particular horse is a male. Actually, we're saying it's a female, because if you look on the man, I'm saying a regular man here has no authority, not an animal, is human, not rich. We're using -1 for male. You can see the only difference between man and woman is that the gender changes, right? Everything else is the same. So a man and a woman, we could just see in the data, is similar minus the gender. Now, when we get to a king, you can see some things change. We give the king an authority. We allow the king to be rich. King is human and male, and the king and queen are very similar minus the gender again. So you're starting to see how these data points are already allowing us to sort of, just even in our visualization, identify things that are similar, okay? Similar in nature. And this is the idea. Now that we've got the data points, I could display all that on the screen, and we're going to do that. But we need a way via an algorithm to determine how similar two data points are. And this is where the idea of something like cosine similarity comes in. There's different types of algorithms that we can use to take a set of data points and look to see how similar they are. The most common one that I've seen is the cosine. So if I go to our vector package here under foundation, where that similarity function is, okay, you'll be able to come in here and see that what we're doing is a cosine similarity call here. So given a target data and a set of data points, this function is going to return a similarity score and a similarity percentage for each one of them, using that algorithm right there. So if you're a math whiz and you're looking at that, maybe your eyes are going, yeah, of course, Bill, there's cosine similarity right there. My brain looks at that and says, okay, I'm glad it works. That's where we are here. And this little package has the ability to also let you add vectors and some other things for your own sort of purpose if you're going to be using any of that. But right now, what I care about is running some of these vectors through this function to see how well it's able to identify the similarity of the data that we've sort of produced. So we'll range over this, and we'll make each data entry a target against all the other entries. It should always be 100%. Should always be 100% for itself. So we're going to make sure that happens right there. Let's do that first. I'm going to comment out all of this right now. I don't want to get into that. Let's just run this right here and see what happens with the data that we've identified right there. So that's example 1. So I'm going to come in here and do make, and you can run this at home too, example 1. And I'll make this a little bigger. So if you notice again, now I've displayed our data points for the horse, man, woman, king, and queen. There they are. And then I run each one against all of them. Now, let's take a look at this, right? Like, we expect a horse compared to a horse to be 100%. But if you look at horse compared to a man, we have a minus 50% similarity. And okay, that's fine. I mean, that means that a horse and a man is pretty far off. Now, because our data set is so small, When we try to compare horse and woman, we get a 50% similarity. And that's only because our horse is female and the woman is female. I mean, that's it. So you could see here that only having 5 data points really doesn't accurately describe the similarity of things. And this is why when we start using some of the LLM stuff, you'll see that we'll get up to 512 or 1024 sort of data points of similarity. And one could argue that the more data points of similarity, the more accurate it could be. Of course, there's a point of diminishing return, depending upon the data that you're working with. But I think you can get a general understanding of that. If you look at comparing man to everything, this is good that it's the same. But comparing a man to a woman, we have 0% similarity. It makes sense, at least for the data points that we've done, because everything was sort of, again, based on that. Now, this one gets super interesting to me because when we compare man and king, we get a 70% similarity. I kind of like that. It makes me feel good that our algorithm is even for this small data set is sort of working, right? It's just the same thing we see with woman and queen, right? There's a 70% similarity with that. Okay, so you could see here that even with our small 5 data point system, with our 5 data point vector, that we're able to get some accuracy around the fact that a woman and a queen are 70% similar, a man and a king is 70% similar. And you can see how this could begin to start working. There's this sort of classic test that I saw online as I was learning this stuff about this idea that if you take a king, subtract a man, and add a woman, that should be similar to a queen. Okay, so the idea is you take a king, subtract the man out of the king, and then you add woman to the king, then we should have something that's similar to a queen, right? And this is this sort of classic test, which is why our vector package has the idea of subtraction and adding, so we can sort of play this math game. So if this is a good sort of test if you're playing with your own sort of embeddings and you want to see some of this stuff work. So what are we going to do then? Data point 3 is here, data point 1, assuming 0, 1, 2, 3. So man and king. Man is 1, king is 3. So I'm saying subtract king from man. We get king sub man. And then I say take the king minus the man and add the woman vector to that. So we end up with king sub man plus woman right there. And then we take the vector for the queen and we do a cosine similarity. So let's see what happens here. Let's see what that percentage is as we subtract man from king and add woman and then compare it to the similarity of a queen. And pretty cool here that we get 100% similarity at that point, right? And that's kind of what we're looking to be able to do here. So this tells me that our cosine algorithm is working pretty good. Our data points are super small, right? And that's why we're getting 100% here. They're super small, but it does show you this one little example I think was great for me because it started to sort of give me the semantics on what it meant to take a piece of data, vectorize it, and then leverage these sort of algorithms like the cosine similarity to get a general sense of which data points are similar to the others. And then you saw me doing some vector math with adding and subtracting that gave us the ability then to see how things, when added and subtracted, were similar to each other. But like I said, this is, I would argue, really a toy program just for learning. You're never going to hand code your own embeddings because you need really hundreds, if not 1,000 sort of data points. And so this is where the LLMs are going to come in. We'll have specific large language models just for embedding. So what I want to do in the next video is try to leverage the same example, right? We'll take our 5 data points, but instead of us generating the vector embeddings, we'll ask an LLM to do it. and then we'll run the similarity functions again and see if leveraging let's say a generic embedding model gives us similar results. And if it does, that's good, because that's what we want, right? We don't want to figure out what the feature sets are ourselves. We just want to say, here's some data, vectorize it, here's some data, vectorize it, and then hope that the similarity holds true, because that's going to give us the ability to do some powerful things later.